Hi everyone, welcome back to our channel. In the last video, we have discussed on fundamental theorem of arithmetic and the solutions to exercise problems 1.1. If you have not watched it yet, please do watch and do comment if you have any doubts. In this video, we will be discussing on section 1.3, that is revisiting irrational numbers. So without any delay, let's get into the video. Let's discuss the theorem 1.2. Let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. So let me explain this theorem with an example. Say 625 divided by 5. We are supposing P as a prime number 5. 625 divided by 5. So 625 is divisible by 5. Let me write 625 by 5 as 25 square divided by 5, as 25 square is equal to 625. So here P is equal to 5 and A square is equal to 25 square. So from the theorem it is given if P divides A square, that is if A square is divisible by P, it is divisible, right? 25 square is divisible by 5. Then what happens? P divides A, that is A will be also divisible by P. So A square is equal to 25 square, then A is equal to 25. We are taking the square root on both sides, we get A is equal to 25. So 25 is also divisible by 5 and it is true, right? 25, we can divide 25 by 5, where A is a positive integer. Yeah, we have taken A as a positive integer. So I have just explained this theorem with the help of an example. Proof. So let's write A as the product of its prime factors. So let prime factorization of A be as follows. A is written as the product of its prime factors, P1 times P2 times etc. Pn, where P1, P2, etc. Pn are prime numbers. Therefore, A square is equal to P1 times P2 times etc. Pn the whole square, which can be written as P1 times P2 times etc. Pn times P1 times P2 times etc. Pn, which gives P1 square times P2 square etc. Pn square. Now given in the theorem that P divides A square. So given that P divides A square. So according to the fundamental theorem of arithmetic, if P divides A square, then P is one of the prime factors of A square. So according to fundamental theorem of arithmetic, if P divides A square, then P is one of the prime factors of A square. Prime factors of A square. However, using the uniqueness part of the fundamental theorem of arithmetic, we realize only prime factors of A square are the only prime factors of A square are P1, P2, etc. Pn, are P1, P2, etc. Pn. And we can say P is one of the factors of A square and P is among P1, P2, etc. Pn. Since we know that A is equal to P1 times P2 times etc. Pn, or A can be written as the product of its prime factors P1, P2 etc. Pn, P divides A, as P is among these prime factors. P is among these prime factors. We can say that P divides A. Hence, this theorem is proved. So this theorem is a very important theorem from the exam point of view. We have to prove that root 2 is irrational. So to prove this theorem, we are using the technique called proof by contradiction. That is, we are assuming to the contrary that root 2 is a rational number, and then we will prove that root 2 is irrational. So let's start. Let us assume to the contrary that root 2 is a rational number. So we can write it in the form of P by Q, where P and Q are integers and Q not equal to 0, because rational number is a number which can be represented in the form P by Q, where P and Q are integers and Q is not equal to 0. So we can write root 2 as P by Q. Suppose P and Q have common factors other than 1, then we should divide both P and Q by the common factor to get co-prime integers. So suppose P and Q have common factor other than 1, then we divide P and Q with the common factor to get co-prime integers. A and B. So co-prime integers are those integers which have only one common factor, that is 1. So let's write root 2 is equal to A by B, where A and B are co-prime integers. So let's rearrange this and write it as, let's take B to the other side. So B was denominator on the right hand side. When it moves to the left hand side, it becomes the numerator. So B root 2 is equal to A. Now squaring on both sides, we get B root 2 the whole square is equal to A square, which gives B square, 2B square is equal to A square. That is, B square is equal to A square by 2. This, therefore, 2 divides, sorry, let me wrap this. Yeah. So 2 divides, therefore we can say 2 divides A square. So from theorem 1.2 we can say 2 divides A. If 2 divides A square, then 2 divides A. That is what theorem 1.1 states. So we can write A as the factors of 2, right? So 2 into some integer C. For some integer C. Now substitute A is equal to 2C in the equation. Let's say this equation as 1. In equation 1, we get 2b square is equal to 2c the whole square. So we get 2b square is equal to 4c square. B square is equal to 4c square divided by 2, which is equal to 2c square. So c square is equal to b square divided by 2. That is, we are taking 2 to the other side. So 2 was numerator here. When it is taken to the other side, it becomes denominator. So we can say 2 divides b square. So by theorem 1.2, we can say 2 divides b as well. So if 2 divides b square, then 2 divides b by theorem. So therefore, we can say both a and b have 2 as a common factor. As a common factor, which contradicts the fact that a and b are co-prime. Therefore, we can conclude that root 2 is irrational. This is what is known as the proof by contradiction. First, we assume that to the contrary, that root 2 is a rational number, and then at last we found that root 2 is a irrational number. This is what is known as proof by contradiction. Let's move on to the example problems. Example number 5, prove that root 3 is irrational. This is similar to how we have done root 2 is irrational. So this proof is based on a technique called the proof by contradiction. So let us assume to the contrary that root 3 is a rational number. A rational number is a number which can be represented in the form p by q, where p and q are integers and q not equal to 0. So we can write it in the form, p by q, where p and q are integers and q is not equal to 0. So we can write root 3 as p by q. Now suppose p and q have common factors other than 1, then we divide both p and q with their common factors to get co-prime integers a and b. So if p and q have any common factors other than 1, we divide both p and q with that common factors to get the co-prime integers a and b. So co-prime integers are those whose common factors are 1. So we can say root 3 is equal to a by b. So let's take b to the other side. So b it was at the denominator in the RHS. When it moves to the LHS, it becomes numerator. So b into root 3 is equal to a, squaring both sides, b root 3 the whole square is equal to a square, which means 3b square is equal to a square, since root 3 the whole square is equal to 3. So 3b square is equal to a square, b square is equal to a square divided by 3, which means 3 divides a square. So by theorem we can say if 3 divides a square, then 3 divides a. Okay, so we can write a as a factor of 3 for some integer c. So let me, okay, so we are substituting a is equal to 3c in equation 3b square is equal to a square, that is here this equation number 1. So we are substituting 3 equal to ac in equation 3b square is equal to a square. So this becomes 3b square is equal to 3c the whole square. So 3b square is equal to 9c square, b square is equal to 3c square. 3 cancels 3. So b square is equal to 3c square. C square is equal to, we are taking 3 to the other side, it becomes b square by 3. So we can say by theorem, so here we can say therefore 3 divides b square. So by theorem we can say if 3 divides b square, then 3 divides b. Therefore a and b have at least 3 as a common factor. Now we know they have at least 3 as a common factor, which contradicts our assumption, which contradicts the fact that a and b are co-prime or co-primes. This contradiction has arisen because of our incorrect assumption that root 3 is rational. This contradiction has arisen due to our incorrect assumption that root 3 is a rational number. Therefore, we can conclude that root 3 is irrational. Hence, proved. I hope you understood this problem. Let's move on to the next example. Example number 6. Show that 5 minus root 3 is irrational. So we are proving this using the proof by contradiction. So let us assume to the contrary that 5 minus root 3 is a rational number. So we can write it in the form p by q, where p and q are integers and q not equal to 0. Suppose that p and q have only one common factor, that is 1. We are taking them as the co-prime integers. So we can write 5 minus root 3 in the form of p by q. So let's write, let us assume to the contrary that 5 minus root 3 is a rational number. So we can write it in the form of P by Q, where P and Q are integers and Q not equal to 0. Suppose P and Q have common factor other than 1, then we divide both P and Q with the common factor to get the co-prime integers. Thus we cancel out the common factors from both P and Q and make P and Q as a co-prime integer. So let's write 5 minus root 3 in the form P by Q. So let's rearrange this equation in such a way that root 3 is kept on the left hand side and 5 is being taken to the right hand side. So we can write this as 5 P by Q, we are taking it as from the right hand side to the left hand side, and root 3 is being taken to the right hand side. So 5 minus P by Q is equal to root 3, which is also equal to root 3 equal to 5 minus P by Q. This can be also written as root 3 is equal to 5 minus P by Q. This can be written as 5Q minus P by Q. Since P and Q are integers and Q not equal to 0, we can say 5Q minus P by Q. We can say 5Q minus P divided by Q is a rational number. If 5Q minus P by Q is a rational number, then what happens? Then we should say root 3 is also a rational number, which contradicts, as we have already proved in the last example, that root 3 is irrational number. So from here we can say, so root 3 is also a rational number as root 3 equal to 5Q minus P by Q. But this contradicts the fact that root 3 is irrational. We have already proved that root 3 is an irrational number. So root 3 being a rational number, this contradicts. So this contradiction has arisen. Because of our incorrect assumption that 5 minus root 3 is a rational number. Therefore, we can conclude that 5 minus root 3 is irrational. Okay, hence proved. So I hope you understood example number 6. Let's move on to the example number 7. Example number 7 show that 3 root 2 is irrational. So we are proving this with the help of proof by contradiction technique. So let us assume to the contrary that 3 root 2 is a rational number, so we can write it in the form p by q, where p and q are integers and q not equal to 0. Form p by q, where p and q are integers and q not equal to 0. Suppose p and q are, let's suppose p and q are co-prime and q not equal to 0, then we can say, then co-prime means those that have only one common factor, that is 1. If p and q have any other common factor other than 1, then we divide both p and q with that common factor and make it co-prime. So we can say then 3 root 2 is equal to p by q. We are rearranging this so that root 2 is kept on one side and the rest is taken to the other side. So it becomes p by 3q. This is for the ease of proving this problem. We have kept root 2 on one side and have taken the rest of the value to the other side. Now the LHS becomes root 2 and RHS p by 3q. Since p, q and 3 are integers, we can say p by 3q is a rational number. If p by 3q is a rational number, then root 2 is also a rational number. But we have already seen that root 2 is an irrational number. So this contradicts the fact that root 2 is irrational. So we can conclude that 3 root 2 is irrational. So that's all for today's video. I hope you understood the concepts. If you have any doubts, please put your queries on the comment section. Thank you.